These are some of my favorite math stories. In this episode, Mathematics Is Sharkovsky Tank, we look at a truly remarkable result known as Sharkovsky's theorem. This is, like the title, a little more technical mathematically than most episodes, but I think you'll find it worthwhile. We need to review iterates of functions, see the chaotic episode. When we say, for instance, that f of x equals x squared minus 2 has a 3-cycle, we mean that there are three numbers, a, b, and c, whose iterates form a loop. F of a is b, f of b is c, and f of c is a. For example, on a 12-hour clock, if the function is 4 hours later, f of 1, 4 hours later from 1 is 5 o'clock, 4 hours after 5 is 9, and on a 12-hour clock, 4 hours after 9 is back to 1. Now we'll take a huge detour and look at orderings of the positive integers. For our purposes, the term listings is probably more helpful than orderings. The ordering that you're familiar with does in fact list the positive integers in order, 1, 2, 3, 4, 5, 6, and so on. Are there other ways to list them? Yeah, you could, for example, put all of the even integers first, and then list the odd integers, 2, 4, 6, 8, etc., and then 1, 3, 5, 7, and the rest. This ordering has disadvantages. It's unfamiliar. Okay, weird. It's not what you normally mean by order. If we were talking through the list, we would never reach any of the odd numbers. Nonetheless, all of the positive integers have a place in this listing. If this was a courtroom drama, an attorney would be standing up now and saying, "Objection, relevance." I'm sorry to say that there's worse to come. Here is Sharkovsky's ordering. Named for O.M. Sharkovsky, born in 1936, died in 2022, was a Russian mathematician. So start with the powers of 2, but place them at the end in reverse order. So our ordering is going to end with 16, 8, 4, 2, 1. At the beginning of the list, put in all of the odd integers greater than 1. So we're going to start with 3, 5, 7, 9, and so on. After the odd integers, put in the odd integers times 2. So we'll put in 6, 10, 14, 18. And next come the odd integers times 4, 12, 20, 28, 36, and so on. Then the odd integers times 8, then times 16, and so on. We now have an infinite list of infinite lists. Crazy, right? But every positive integer is in this list exactly once. Every integer has some factors of 2, and what's left is an odd number. We'll call this an ordering because it lists the positive integers in a particular order, in the sense that given two positive integers, we can say that one of them comes before the other one. So 6 is before 28 in this list, 31, an odd number, is before 12, 88, 8 times an odd, is before 8, and so on. Still weird, but it does make sense, right? So here is Sharkovsky's theorem in two forms. Assume that the integer m comes before the integer n in Sharkovsky's ordering. If a function f has an m cycle, then it also has an n cycle. If a function does not have an n cycle, then it does not have an m cycle. You might recognize that versions 1 and 2 are logical equivalents of each other. The mathematical term for them is contrapositive. Let's see what they can tell us. We can show that f of x equals x squared minus 2 has a 3-cycle. The approximate values are negative 0.445, negative 1.802, and 1.247. In Sharkovsky's list, 3 is before 14, so the theorem tells us that f also has a 14-cycle. 3 is before 16, so x squared minus 2 also has a 16-cycle. In fact, 3 appears first before every other positive integer, so version 1 of this theorem tells us that f of x equals x squared minus 2 has cycles of every possible length. It has a 359 cycle, and a 2,714 cycle, and so on. That's pretty amazing. By contrast, you can show that f of x equals x squared does not have a 2-cycle. Since every integer other than 1 comes before 2 in Sharkovsky's list, version 2 tells us that x squared does not have any cycle other than maybe a 1-cycle. And FYI, it does have 1-cycle fixed points of 0 and 1. We can gain a lot of information about the cycles of a function just by solving for 2 cycles or 3 cycles, if we get lucky, that is. Suppose we have a function for which we find a 2-cycle and then prove that it does not have a 3-cycle. This time we don't get anything else for free. Since 7 is after 3, for example, I can't use version 2 to say that my function does not have a 7-cycle. And since 7 is before 2, I can't use version 1 to conclude that the function does have a 7-cycle. Now, when I first saw this result, I wondered what caused Sharkovsky to come up with such a crazy ordering. It is incredible, isn't it? By the way, if you have studied chaos theory, period doubling bifurcations gives a partial explanation. In practice, knowing which cycles a function has or doesn't have can be very useful. But I mostly love this as an unexpected and comprehensive solution of a problem. That is awesome.